All right. So this weekend, I basically spent most of it working on the algorithm. So I basically got everything working in Python, and unfortunately, it was just by essentially copying uh, word for word the book over. Also, I switched the text examples from using the actual physical hard copy of this book over to using the digital version that I got alongside with it. I just started doing that because I noticed that there was a few times in a hard copy that they were using slightly different methods for, and there were some small bugs, but those were for the most part fixed on the web version. So I'm able to work with that a little bit. So what I have here, and so I attempted to re-implement everything in this Streetlight Double Network JS, and so I think, yeah, I basically tried to get this all working, and it runs, but the errors don't go down towards zero, so it is not working the way it's expected. So I do need to fix that. Miguel, good morning. So I think that's going to be what I'm working on today. So the plan is still the same. We have a week and, I mean, essentially a week and a business week. So what, like 10 days or so until my conference talk. It's not really a real conference talk. It's more of I'm going to be recording a video slash live streaming if the network is good enough for 45 minutes. And so during those 45 minutes, the plan is to implement the functions that I need and then play a game of Pong using that the AI that we create. And so I want to have everything sort of set up, all commented with and test driven. So that way on the day of, it's going to be very easy for me to write it and verify that it's working properly. And of course, a backup solution that I can switch to and say, hey, I promise I was able to get this working would be nice too, in case everything just goes sideways. So, this entire thing wasn't really working out too well. I switched over and started working on a branch to redo this all over again from scratch. And I'm calling this using. I started trying to use a library. I found. There's no Chromium. I found a library, a math library, that does vector math and matrix math called Math.js. But something that I also noticed when I attempted to just use Math.js as a essentially direct replacement for NumPy is that Math.js and NumPy are not compatible with each other. They do different things, or at least they work in different ways. So, for example, in we can create a matrix just like NumPy here, so we can see that. And we can add and multiply and subtract matrices and arrays, which work really well. But when we do the dot function, it refuses to work between a vector, so just a standard array, and a matrix. And it does that because the sizes are different. It needs them to be exactly the same size. So it can do, I believe, a dot between well, actually, no. I think a dot in Math.js can only be done between vectors. And if I go down to the bottom here, there's a full functions page. And math.dot. Calculate the dot product of two vectors, which is, I mean, so it gives an example here. And it's just two arrays, two vectors, two dot and numpy, however. So let's go to numpy dot. It's a little bit different. This is not the actual documentation. Where's the real documentation? There's so many guides explaining what it's doing, and I was skipping most of them. I had it before. Let's see, numpy. Is this it? Is this actually the documentation for numpy dot? It might be. So numpy dot, as Katali had sent to me a little bit earlier, is doing different things depending upon the size of the vectors or matrices that are being passed into it. So I ran a quick experiment the other day. So if we import numpy as np, all right. So if I say like we'll just say our like inputs. And we make this a simple array. So it's going to be something like 1, 2, and 3. So a vector. And then we have our weights. And this is not a simple array. This is a matrix. So let's say we have this 1, 2, 3, 4, 5, 6, 7, 8. So initially, I thought that this was impossible because I thought what was going to happen if we dotted this was that we'd take 1 times this 1 plus 2 times this 2 plus 3 times this 3. So basically this vector, so the first vector in the matrix, weighted sum with this vector. And I think that's how it works in just a vector dot. But this is a matrix vector dot. And so if I np dot inputs and weights, instead we get a for long vector out, and it's actually 1 times 1 plus 2 times 5 plus 3 times 9 for this first number. So it's going down the rows in the first column, and then repeats on the second column, and so on and so forth for as long as this is. And my function, I just changed it to be that way in this branch. But it wasn't doing that. It was looping through the matrix, taking the first item. And so I needed to have the matrix set up differently. So it's been a little bit annoying to sort of assume that NumPy is doing what I think that it's doing, and then find out that it's actually doing a lot more. But I'm learning the math, a little bit. Okay, so that's my 10-minute long spiel on where we are and what's been going on. So where I'm currently at right now is I've just been updating these errors. So I can run this code, and I'm currently creating one set of streetlight data, so one streetlight, and I'm looping through all of them one time. I created a function. Where is... yes, here. I created a function here that generates the streetlight data for me. So I can actually have it create 1,000 streetlight configurations, and it will calculate the correct outputs and give me the same number of testing data. So I can use that to verify, like, hey, is this actually working? And it is using just a math.random here. So hopefully it will be, I mean, I'm also rounding it, so it is a real number, not a fake number. Not a fake number? No, not a floating point number. An integer. Okay, so let's go over this pretty quickly of what I have. We're going to grab our inputs, both the testing and the training inputs. We're going to set our alpha. We're going to set the hidden size of the network. So that's going to be the number of outputs from the first neural network, and therefore the number of inputs to the second neural network. Then we set our layer 1 weights. So this is where it was getting a little bit interesting, where I wanted to set. Also, I realized that width and height for a matrix is probably like not the right syntax for creating this. In fact, I think it might be backwards, where it's down first, and then so it's the number of rows, then number of columns. But I'm hoping that this is readable to anybody who sees it. It makes sense in my brain, which I guess is good for me. But so this is 4 columns, and then we're going to have the number of items in the street light. So that would be 3, because there's like, one light, one light, one light. So that's our first set of weights. It's a full matrix. Our second set of weights is going from a 4 in to a 1 out. And since the number of things coming out from the product is going to be 1 wide, so 1 column and 4 rows. That's what I have here. Actually, I have yes, I have one column, 4 rows. Yeah, Miguel. The linear algebra, it does seem to be very strict, and it's very interesting to sort of struggle my way through this, but also at the same time, I'm probably learning it a lot better than if I just read the solution online and then implemented that. I would never remember it or understand or know why. Okay, so then we have our weights. Our second, so this is the weights to translate the neural network from to the final prediction. So then I begin looping through, and this is going to be like, how many times am I going to repeat the entire data set? So right now it's just 1 time. We record the number of errors we've had over the 1 full set of data sets. And then we begin looping over every single streetlight instance. Right now, because we have 1, this is just happening once, and this is just happening once. All right, so coming into here. First of all, I started using the syntax of the book just to make sure that I was copying it correctly. I wanted to just call these like, the current streetlights. But so this is layer 0, which is basically the inputs to the first neural network. And so I grabbed the first set of inputs. Layer 1 is the result of running the first neural network. So it's a dot vector matrix between the inputs and those weights. So this is where I had to switch over And where is my... dot vector matrix. I had to switch the math for this. So I am a little bit upset that Prettier keeps on doing this to me, and I like it and I don't like it. I don't like it for these matrices because I want to see it like what it actually is. But other things I'm perfectly happy with. I may have to switch to something else. Okay, so this is basically, I had a completely different configuration last time to test, and therefore the tests were passing, but I changed it up. We're now dotting the vector and the first column, and then the vector and a second column, and so on to get this output. And the way that I'm doing that is actually transposing. So I just say, well, what if I just transpose and then I run what I have as a dot of two vectors, and then that worked. Well, transpose was something new also. I hadn't written that either. So let's go take a look at transpose. Transpose, I think I actually have this. Yes. I went up and looked on Wikipedia for transpose so that I didn't like make any mistakes with this. And so here is the GIF file that sort of describes what's happening in transpose. Basically, you take the first column and that becomes the first row. And then the second column becomes the second row, and so on and so forth. And so that's exactly what I've done here. So in this test, we have I have two transpose tests here. One is just a simple array. So it's a one column, 4 rows, and that becomes 4 columns of 1 row. And then over here, I have 1, 2, 3 columns of 2 rows, and that becomes 2 rows with 3 columns. Yeah. Hello, good morning, Katali. And so I've got transpose working, and that's actually helpful in reconfiguring the matrix to be exactly what I was expecting it to be for the dot, dotting a matrix. Now, whether or not that's still exactly what NumPy was doing, that remains to be seen. I have to like finish this neural network using these new functions, and then hopefully everything is working the way it is. Other functions that I've created are the ReLU and the ReLU to derivative. I named them just the same because I'm relying completely on the book for understanding what it is, and I don't really understand the why yet, just the what. So it's going through, and anything that's a negative number or a 0 is converting that to be a 0. And anything that's a positive number stays the same. And a ReLU to derivative is changing anything that's a positive number turns into a 1, and anything that's a negative number turns into a 0. So I have these two functions as well. Also, I have no idea what I did to save that, so I am not going to save. Let's go back to you. And so finally we have where I'm updating the errors for this. Right. I mean, so it's to turn off the neurons. And I kind of get that. I don't fully get the why of like why we're turning off negative numbers. It explains, the book explains the why, but I haven't really grokked it yet. So I think it's just like more experimentation with it, and then it'll sort of like start coming to me. Maybe also other sources of learning will also help. Like once I go through this, then I can go through other resources, and then eventually it'll like click. And so this is where I am. I have my layer 2 errors, and when running it, I get this is the error. All right, so fine. Let me pull up the book over here. So the next thing to work on is setting up this layer 2 delta. So basically it's saying we're going to take layer 2 and subtract from the what actually happened. So let's do that. Const okay, so what they have is layer 2 subtracted from, I don't know why they really put this, they put this into parentheses, which is not necessary when there's just a single instance of this happening. I think probably because it was copy and pasted from this here. But basically, I'm going to do this exact same thing. I just don't need to multiply it to the power of 2. I'm grabbing the first item in an array because this is just an array of 1, and this is an array of well, once I grab this, then it's that entire thing. So let's console log this. So here is the delta. So then it wants us to get the layer 1 delta. And so this is where it actually gets a little bit interesting. So the layer 2 delta is that like the final delta, the final prediction difference. To get the difference for the hidden network, so that's that output from the first neural network, that's right here. We need to do a dot between the layer 2 delta, so this, which is interesting because it's just a number, and weights, the second set of weights, which then they transpose. So this is a place where I can get a little bit, I can get it wrong. And I think they're doing this that way we can get layer 1 delta needs to be the same shape as the weights, as these weights. That would be 4 columns and 3 rows. So we have layer 2 delta, which is a scalar. And as far as I can tell, this means that it's just multiplying. So scalar vector, scalar matrix. The weights 1, 2 is not a matrix, is it? Or is it? Let's find out. So layer 2 delta is going to be on the left, and we're going to put layer 2 weights on the right. So this is the layer 2 delta, and this is the weights. So it is a matrix with 1 column and 4 rows. Is that correct? Is it printing the way that I'm expecting it to be? So that's yeah, it's 1 column because there's only 1 item in each of these arrays, and then down 4. So four rows. And that to me feels like it's a scalar matrix multiplication there. Except I need the layer 1 delta to actually end up looking and having the same shape as the layer 2 delta. Now, what I can do is go into the solution.py, which I've been doing this to sort of see what is actually going on in the solutions. This is actually just fully implemented from the book. And I've been printing out individual pieces so I can really know what's going on. So at this point of time, this is what we're trying to implement here. So before this, we're going to print layer 2 delta, and weights 1, 2. Now it's interesting, they transpose these weights before doing this. So let's see why. Of course, it is in the solution. So layer 2 delta is, I mean, I guess we can call this a matrix. It's an array with 1 column and one row. Hold on, I've got a little bit of weird noise coming in from the outside. I'm gonna go close the door. All right, I'm back. And then for weights 1, 2, we have a matrix with 1 column and 4 rows. So I kind of feel that I have that, except this is a scalar for me right now. And this is exactly what that is. But they transpose this. They transpose this because in the matrix dot, what ends up happening is that it's this multiplied by the first item. It goes into the first one, plus this one by the second item. I think that's what's happening. So let's do a .t to this. And so now this can be this times this, the delta times this one, the delta times this one, and so on. And now if I comment you out, I don't want to run this ReLU to deriv, so I'm going to delete that. Actually, I can just do this temporarily. I want to see what the result of dotting layer 2 delta with weights. Okay, so it's just a 4-column, 1-row matrix. So that's what I need to do at this point in time. So our layer 2 delta and our layer 2 weight. So let's remind ourselves what this is. We have our appropriate matrix. This is not. So I'm going to need to convert this into a matrix, which I believe is simple enough. I can. Is that one? No, it's this one. I can just go like that. And then you need to be transposed. So transpose. All right, I don't know how I deleted that, but it's back. So now I have my matrix here for that, and I have, did I not do this correctly? In the Python, oh, it's not showing what I wrote previously, is it? That's interesting. I need this to be 4 arrays. That's what I need this to be. So not 1 column, but 4 columns of 1 row. So console log. Let's try this again. So the first one I think is fine now. The second one needs to be the, yeah, 1 row, 4 columns, yes. And it's the second weight. So there's this first layer 2 delta, that's in the correct formation, and you are, oh, wait. I think this isn't the correct formation. It is, no, wait. I'm now trying to think about this. This is 4 rows and 1 column. This is 4 rows and 1 column, and I need it to be 4 columns and 1 row. So essentially, just like this, with spaces or commas between them. So let's transpose layer 2 weights. Yeah, so like the way it's printing out is very, very hard to sort of like wrap my mind around. Like, is this correct? Um, this is a single. This is now 4 columns and a single row. Also, my layer 2 delta is weird right now. Okay, good. It's not just like purely 1 or -1. So I think this is correct. It will yell at me if it's not. So I'm gonna start with this by saying, okay, const layer 1 delta is equal to, we're going to do a dot I think it's just going to be the dot vector matrix. I don't need both of these, just a single vector. So that's going to be the layer 2 delta and the transposed layer 2 weights. Layer 1 delta is now going to be printed out. Cannot read property 0 of undefined. Okay, so I think that means the shape is wrong. So I think you might be right, Miguel. Let's try not transposing and seeing if it's happier. No, still unhappy. So it's actually something else completely. That is in this line, right? I didn't do something else. No, it is right here. So a dot vector matrix. Oh wait, what did I do there? Oh, I screwed that up. Okay. Transpose layer 2 weights. Then show this off. There we go. So this is the result, which is compatible with the result that we saw if we're running the Python. So it is a matrix and we got a vector out. We can deal with that if necessary. And then they want to multiply this. You need to put that inside an array. So yeah, I can then take this and just put that in an array here. And now I'm getting exactly what we're getting here. Okay, so if I work with 4 of these, then it will be exactly the same. All right, so then they have this, the ReLU, so they're multiplying this matrix by the ReLU to derive. So let's see what happens. I think what that means is that some of these turn to 0, the negatives turn to 0, and the positives remain the same. That's my my reading of it. No. Also, I'll turn you on. All right, so let's re-add you in here. And now we'll see what layer 1 delta becomes. Yeah, so we have zeros and, funnily enough, negative zeros. Oh, that's interesting. The negative zeros have decimal points. I didn't think that that was going to happen at all. So I thought what was going to happen was, yeah, that shouldn't be there. That's sort of my thought. Now if I don't have this, if I like reset, we need to go through, let's say, the 60 times that they were. The error is approaching 0, so it's exactly like what the code was having. But I find it's interesting that at least like my Python that I have, Python 3, is doing this. I actually haven't run this with just Python 2. Oh, because I need to pip. Oh, I didn't install like pip 2. Okay, well, we're sticking with Python 3 then for right now. But that is fascinating and a little bit disturbing at the same time. I don't know why it would be doing that. I don't know why it works when it's doing that either. But correct me if I'm wrong. It is supposed to be turning all of these negative ones into 0 to turn them off. And all the positive ones stay exactly what they were. Yeah, okay, so that's what I thought. So I've got an array of array. I've got a matrix here. Negatives go to 0 and positives stay. That's what I thought. So now I'm going to take this and I'm going to ReLU to derivative this result, and then we're going to take a look at this again. And with a derivative form, well, right, because I'm converting it. Oh no, it's that's not right. I'm not actually converting this like that. I'm multiplying it, doing a matrix multiplication. So because it's multiplying of a ReLU to deriv of layer 1. Okay, so we have this. This is a matrix. Let me make sure I didn't screw this up. We have a matrix with 1. Oh, I have 4 of these. Let's put this back down to 1 again. We have a matrix with 1 row and 4 columns. Yes, Miguel. What's weird is that in the Python version, it's not a pure 0. So I don't know what that is or if it's causing an error. It seems to be working still, and I did over the weekend implement the testing, so like to figure out is it actually working, and it got to 100%. So the neural network seems to be working in Python, which makes sense. Nobody online in the online forums were complaining that the code wasn't working. It was they're complaining about other things. All right, so we need ReLU to deriv of layer 1, and it needs to be the same shape as this. So let's do that here. So this is just purely the layer 1, which is the first prediction, so the hidden prediction. And if we take a look at this, it's just a vector like that. So I can turn this into another matrix and then do matrix multiplication on it, or I could not put the array around this and then do vector multiplication. Either way should work, but let's try this. So we're gonna do, we have that. We're now gonna do matrix. Oh, I don't have that pulled in, do I? I don't have matrix multiply, do I? Let's add that in. And so then also deep learning functions. Let's just double check with this outline. Yeah, we don't have matrix. We just have matrix subtract, but not, and I see it like a dot and a dot vector matrix, but a not like matrix multiply. Yeah, so let's add that. Matrix multiplication is just mapping through one matrix and vector multiplying it with the other matrix at I index. Yes. So that's, I mean, kind of what I'm going to do. I'm going to be using all of these other functions as part of it, but that way I can have the names correct. And I can test it properly. So. So it should multiply two matrices of the same size, of the same shape together. All right, so our input, so matrix 1 is going to be, let's just say 1, 2, 3, 4, because that's kind of what we have. And matrix 2 is going to be 5, 6, 7, 8. Our expected output is going to be another matrix with just like these multiplied together. So this will be 5, 12, 21, 32. All right, so we'll come back down here and MPX. Okay, so it's not working yet, but that's because it's undefined right now. We will now implement this. So Katali, you have the suggestion, which is we map through the first matrix, we get the vector and index, and then we do multiple vector multiplication of the second matrix, which I have I think that's exactly right. So we're going to return matrix1.map. We're going to get the row, and we're going to get the index. And for this row, we now want to do vector multiplication. So do we have vector multiply? That's going to be our row, and matrix 2 of index. And so that should do it. All right, passing tests. We can come back here, pull in matrix multiply, and so now what we're going to do is matrix multiply. So the result of this dot matrix and the result of the ReLU to deriv of layer 1, which is we see right here. So copy you and put you in there. I can't remember if we needed to throw an array. I think we did. Around you. What was my bug on the dot function you told? Okay, yeah, so the dot function, the bug was, I think I actually had this in here right here. The dot function bug that I had was I was doing a dot between these vectors essentially. So when I was creating my my weights, I was saying that I needed to have 3 columns because this is 3 long and 4 rows. But in reality, I needed 3 rows and as many outputs for columns. And so I didn't realize that it wasn't like 1 times 1 plus 2 times 2 plus 3 times 3, but in actuality 1 times 1 plus 2 times 5 plus 3 times 9 for the first item here, and then moving onwards. So that was the problem I was running into. It was just a misunderstanding of how NumPy was dotting a vector and a matrix. All right, so we're doing that. Now let's console log out layer 1 delta. R is not defined. That's the R is outside. All right, so interesting, none. The result of this should be this turned off and be 0. Notice it's -0. Oh no, I mean, this one's been turned off. Those all were turned off. So it's very interesting. We're kind of getting the same results with Python, aren't we? Oh, I turned off all the prints, didn't I? This is the layer 1 delta. Apparently just the errors right here. So let's print out the layer 1 delta. We're going to go back to just one run through of this. That will turn off this print because it will never get to 10. And we can see that it's essentially the same results that we're getting here. We have some negative numbers still. It's not turning them off completely. We have some negative zeros sometimes. And we have positive numbers. And it's in a matrix that is 4 columns and 1 row. So we have that. So that's good. Now, on to the real magic, updating the weights. So are these weights? These weights are created as consts. Now they need to be lets. All right, we're now going to take, this is another fun one here. So here's what we're doing. We're taking these weights and we're going to subtract themselves from the result of multiplying, scaling them down with alpha and multiplying. So there's a lot to unpack here. So let's start with like the very basics. We're going to take layer 1. So that's the prediction. That's the input for layer 2. And we're going to multiply, we're going to dot that against, so weighted sum with layer 2 delta. So let's go and take a look at our, in fact, I am going to put this over there and you get over here so we can take a look at both of them at the same time. You go away so I have more room. All right, so let's take a look at this first. Like, what is layer 1 and what is layer 2 delta? It's layer 1. So there's layer 1, and then so layer 2 delta. Layer 2 delta. So we have a single vector and a scalar. That's what we have. Now, what do we have over here? Like, what are they supposed to be? So I'm going to move this print down to right above this. And we have layer 1. So layer 1 should basically be a matrix of this same shape. Layer 2 should be a matrix of one column and one row. So I can just throw double brackets over these. Are we using layer 1 elsewhere? Dot vector matrix here. So I think just one more to this layer 1. Oh, a set of array. So a set of square brackets, and then 2 for this to turn it into a matrix with one column and one row. All right. So that's gonna be this. So let's do this one step at a time. Also, this looks like it's going to be a matrix dot. Because both of them are matrices. So that's interesting. You think I can do scalar vector multiply. Is that what they're doing here? I kind of want to double check that assumption. So, all right, let's do inputs equals mp dot array. So we know that our layer 1 is 4 items wide. So I'm just going to call this the same thing. So 1, 2, 3, 4. Okay, so that's layer 1. And then we have the layer 2 delta, which is just a single item. We'll just make this 5. Make it a little bit easier in math. Now we're going to say layer 1, and they're transposing it. So they're transposing layer 1, so it will become a single 4 columns. No, it's right now 4 columns. It'll become 1 column with 4 rows. I just want to make sure I get the math right first. So we're going to do this. So then let's transpose this. First of all, layer 1 looks like that. Layer 1 dot transpose looks like this. 1 column, 4 rows. All right. Now we're going to say layer 1 dot. It's just going to be this layer 2 delta. So what have we got here? We've got a single column with 4 rows, and it's taken this 1 column, 1 row matrix and multiplied it by each one. And that's the result. So as long as we get that, then that's good. I kind of want to go into our testing to like actually make sure that this math is remaining the way we want it to be. Let's see, deep function spec. So we have matrix multiply. That's kind of what's happening here. Let's do this again. Yeah, you don't know why he's using dot product since it isn't adding anything. It's just, it's very interesting. And I don't want to say anything negative about data scientists and code that is created, but this is very hard to read code because I feel that dot is not the appropriate. I feel that just a multiplication would have been better here. What would have happened if we had a multi-dimensional array? Thanks. Would it have been, would the dot be appropriate? I don't know. So this is a dot matrix. Do we have that? No, we don't. I know, interesting question, right? Is like, would we want a dot if it was like 2 columns and 4 rows? If you know the answer, I would love to know so that I can make sure when I do my thing correctly, I'm using the right math here. So I'm gonna go ahead and make the assumption that it is correct, and we're gonna create a dot matrix. I guess I'll just call this dot matrix because it's assuming that we have a matrix 1 and a matrix 2. I also love the fact that I'm naming this dot matrix. How many of you had a dot matrix printer? Because I had one when I was a kid, and that was what my parents had given it to me after they got a new one. And so I had this ancient old one, and it shook the entire house every time I printed with it. And it was incredibly loud. Kind of fun to like have the paper in its ream down on a floor in a box, and it would like pull it through in order to print. All right, so deep learning functions, we're pulling in dot matrix. It should, and this is also where it gets interesting. NumPy dot let's actually look at what where it should dot matrices. Is that the multiple term for matrices? To together. I will only right now focus on the one that we see, but I kind of want to know how this works with multiple of them. So if I say, what would this be? np dot so np dot array. I guess we're going to do matrix 1 equals so 2 column. How about like a 2 column 3 row? And it has to be the same shape. But if I have just a single item, so like 10, let's see. Matrix 1 dot matrix 2. Right, wrong shape. I need matrix 2 needs to be 2, it needs to be 4 long, because like 10 times 1 plus 10 times 4 plus 10 times 6. So this needs to be essentially like 1, 2, 3, 4. Oh, okay, so I'm wrong with that. So because I created this as matrix 2. So what do we got? Matrix 1. Oh, that's 3. I only created 3. Okay. So that's not what I expected either, because I thought it was going to be 1 times 1 plus 2 times 4 plus 3 times 6. But I guess that's the, they have to be the exact same shape, don't they? If I make it 2 wide, will that work? No, okay, so I think it has to be aligned 2. They need to be squares, or they need to be like both exactly the same, right? Matrix 1 is 3 by 2, so for matrix 1 dot matrix 2, matrix 2 must be 2 by 3, or 2 by what? And also, I keep on getting confused with what order these are in. So, matrix, which one is which? This is the 3 by 2. So it's 3 down and 2 across. 2 by anything you want. All right. So matrix 2. Let's look at these again. Three is down and 2 is across. So matrix 2 must be 2 down and any number across. Okay, so let's do this again. Matrix 2 equals MP dot array. All right, so 2 down. So that's going to be like 1, 2, 3, 4. So if I do that, matrix 1 dot matrix 2. Okay, so that works. And let's double check our assumptions here. So matrix 1, matrix 2. So this is going to be 1 times 1 plus 3. Oh, wait. Yeah, 1 times 1 plus 3 times 2. That would be 7. And the second one is going to be 2 times 1 plus 4 times 2. So that would be 2 times 1 is 2 plus that's 8. So that's 10. Okay, so that's what's happening. And so if I created it, that's why now the width is more important than the height. Is that right? If I wanted to add more of these, no, okay, so it's not that, it's more of 3, 5. Yeah, okay. Rows 1, columns 1 dot rows 2, columns 2. Well, okay, so it makes sense when it's like they're both the same, like the same shape. When they're slightly different shapes, that's when I get tripped up. And so I need to like see where this is. So this is matrix 1 and matrix 2. And this is the result of dotting matrix 1 with matrix 2. So matrix 1 is 1, and because I thought it was like 1 times 1 plus 2 times 2, but then we run out. So is it really 1 times 1 plus 2 times 3? And that brings it 7 plus 1 times 2. Okay, so that's what it is. It's down the left edges again. So correct me if I'm wrong. I'm going to do this exact one here. So it's going to be const matrix 1 equals. We're going to have 1 and 2, 3 and 4, 5 and 6. And this is going to be 1, 2, 3, 4, 5, 6. I guess an equal signs might be nice. For any matrix multiplication, it must return a matrix with shape columns 1 times dot rows 2. That is a square matrix. I guess like To me, square matrix like sounds like it should be a different thing. Like I feel that that's definitely a square because it's like the same number of columns as the same number of rows. But we saw that a dot of two matrices with one column and 4 rows just results in 1 column and 4 rows. This is what I get for not taking any of those math classes, or rather almost failing all those math classes. And so therefore stopping taking them. Const expected output. I just figure it out at a later time. Okay, so what's going to happen here? And this is where I keep on getting tripped up. Is okay. Matrix 1, it's 1 times 1 plus 2 times 3. So 1 times 1 plus 2 times 4. So that's 1 plus 8. So that should be 9. And then 1 times 2 is 2 plus 2 times 5 is 10. So that would be 12. And 1 times 3 is 3 plus 2 times 6 is 12. So that's 15. I'm relying on you to help me if I get this math wrong. Thank you in advance, everyone. All right, so now 1 times now it's going to be 3 times 1 plus 4 times 4. So that's going to be 3 plus 16, so that's 19. 3 times 2 is 6, plus 4 times 5, so that's 26. 5 times 3 is 15, plus 36, so that's 40, 51. And did I do this wrong? The ones were this first one, 3s and 4s. I think I accidentally did the 5 and 6, didn't I? So hold on. 3 times 1 plus, I can just make this really easy. It's in a matrix multiplication, well, right. But this is a dot, so there's the adding that goes on too. That's not what I wanted. I wanted a calculator. Okay, so this is 3 times, so 3 plus 16, that's 19. 6 plus 20 is 26. 9 plus 24. 9 plus 24 is 23. Yeah. Okay, then 5 plus 24 is 29. 10 plus 30, so that's 40. 15 plus 36, so that's the one where I might get it wrong. 51, so I was correct. We're almost at our time, so I think I'm just going to finish writing this here, and then we'll be good. So that's our expected output. Assert deep equal our dot matrix, matrix 1 and matrix 2, our expected output. And I want to run this one more time, but with what the book is having us do, which is very interesting. So matrix 1, actually it looks like layer 1. Okay, so matrix 1 is going to be, it's transposed. I should probably save that. So layer 1 is 1 column and 4 rows, and layer 2 is 1 column and 1 row. So okay, so 1 column and 4 rows, and can I do, I remember, I don't know how to do like the like the weird select in between there. So this is, we'll just do like 10. So 1 column and 1 row. Our expected output. So what would we expect from this? So it's going to be 1 times 10 plus like nothing. So this is going to be 10. And if we take a look at the result of this, so layer 1.t dot layer 2 delta it's 1 column, 4 rows. So it's just like this. So it's going to be 30, 50, and 60. Okay. So that, let's go ahead and run this, make sure it's failing. So oh, that's interesting. I don't think I had any console logs, so I'm not sure why that appeared. Let's just head out. MPX. Okay. All right, both failing the way we expect them to. So let's come into here and actually make these work. Okay, so what is happening here? We are taking the first row of matrix 1. So if we put this over to the right, the first, so this one, so 1 times 1 plus, no, 1 times 1 plus 3 times 2 plus 5 times 3. I think that's what's happening. I hate that. Did I say how much I didn't like this happening? I need to change that. So it's it's 1 times 1 plus 2 times 4. That's what's happening. I just can't see this when it's side by side. So it's the first item of the matrix. But if we transpose both of these matrices, we should be able to dot 1 times 1 plus 2 times 4. Yeah, if we transpose both these matrices, no, matrix 2 gets transposed, matrix 1 stays the same, and then we dot the vectors from that. That's what we're doing. So we're going to loop through matrix 1. So we're going to return matrix1.map. We're going to get the row and the index. And we're going to return the result of just a dot between the row and the transposed matrix 2 of index of index. All right, first try. Do you think this works? No, it doesn't. Oh, okay. So I was very, very, very wrong. Also, I'm way out of time. I hate leaving at this, but I would need to sit down. I'll probably like think about it right away as soon as I get to work or something. But right, because I need to like, okay, this gets transposed. This is along there. Yeah, I have that documentation up on the right, over here on this like other screen. So I'll figure it out and I'll get it. But unfortunately, I do have to turn off the stream for right now. So what I'm going to do is I'm going to save all of these files. I'm going to push them all up. So let's see. Trying again, but with better math this time. I'm going to push this up. I'm currently in the using a library branch. So I will share this repo with you all. I do have in the VODs, I'm putting in the description for them. Learning, deep learning. And you are over here. Here is that link. All right. Thank you everyone for stopping by. Thank you for all the help. Shakama Gaming, how advanced should I put AI in my video game? I mean, you could put it super advanced and it beats all the players, then nobody wants to play it. And then if it's not good enough, then people get bored and don't want to play it. So there's a nice sweet spot right in the middle there where it's hard but not overcomable. So that's my answer. Also, I'm ending the stream. So sorry for showing up late. Anyways, that's what I've got. Thank you for everybody for coming. I know I'm sorry, but I do have to go to work and I am late. I've got 10 minutes to be able to get ready and head out the door. So with that, I hope that you all have a great rest of your day. My next stream is going to be on Wednesday morning at 6:45 a.m. Mountain Time. And then, and we'll be continuing. We're going to be working on this, so we'll probably not be exactly where we were. All right. See ya. Bye.